Now we're going to be learning about two-column proofs. Before we get into geometric two-column proofs, I want to lead in with algebraic two-column proofs because they are something that you're familiar with and pretty straightforward and simple. So algebraic proofs use they use statements to demonstrate the steps of a proof and reasons to justify each step. So we're going to have two columns here: statements, reasons. The statements show the steps, the reasons justify the steps. All right, we're going to be using a lot of the properties from algebra here. So like APO, SPO, those are just abbreviations for subtraction property of equality, which means we're subtracting something on both sides. These are just properties, mostly properties to make sure that we're maintaining congruence or equality, to make sure that nothing about the equal sign has been affected by us performing operations on both sides. That's what we're justifying. We're justifying steps that we're taking on both sides. All right, so we're given this example, and we're trying to prove that x equals 4. Now, this might seem silly. Obviously, you could just show this, but we're going to lay it out in a proof because our two-column proofs in geometry are almost exactly the same. It's just not showing algebraic steps. They're going to be using geometric properties. We'll get there. Our first statement is always going to be a given statement. This statement is our first statement. X minus 4 equals 3x plus 8. That is a statement that we're allowed to make because it was given to us. Our reason is simply that we were given that statement. We're going to move from that to eventually get down to our provable statement, which is x equals 4. There's obviously a bunch of different ways we can do this. I'm imagining we take out this 3x first. We're going to subtract that from both sides. So our first step is subtraction property of equality. We're justifying it with that property we know to be true. And we can take it away from both sides, giving us 3x minus 4 equals 8. My next step would be to cancel out the minus 4 by adding to both sides. So that's APO. Addition property of equality justifies my next step, giving me 3x equals 12. And then to get that final answer, we're going to divide on both sides by 3 using the division property of equality. So we're showing the steps there and then saying why I was allowed to do it. Well, I know the subtraction property of equality is true, so I'm allowed to do that step. I know the addition property of equality is true, so I know that has to be the next logical thing to happen. The left column shows the step-by-step process. The right column shows the justification for each step. Now it's going to get complicated because it's not going to be algebraic calculations. It's going to be definitions, theorems, and properties that we're familiar with in geometry. So first I just want to break down the different parts and the order that you're going to need to use for a geometric proof. So the parts are the given statement. We also want to make our way to the provable statement, but we're going to do that using these statements and reasons. Those are really the three main parts that I'm talking about. Just whatever information is given to us. You're going to have to state that information in your proof to logically make steps ending with the statement we want to prove. So you're going to take one step at a time, and when I say logically, you're going to see this directly on the next page, but we're going to move from a hypothesis to a conclusion, and then to a next hypothesis and conclusion, and it's just going to keep going back and forth between connecting statements with hypotheses and conclusions. That sounded very confusing, but I promise it will make sense when we get to the next page. The statement is the logical steps of the proof, and the justification, the reason is called the justification for each of these logical steps. Logic is going to tell us what to do next, and you're really going to just move from one conditional statement to the next. We have three different reasons that we could use in this class. First one's called definitions. These are biconditional statements. So they are if and only if. Basically, the converse and the conditional must be true. So we just call it a definition just to simplify it. The definition of supplementary angles. We know that they add up to 180. That's what we call supplementary angles. Usually that's why we set up a definition. It's just so that we can use a term and everybody agrees on what it means. If we know that angles add up to 180, then we know they're supplementary. If we call them supplementary, then we also know that they add up to 180. A theorem or a postulate, those are probably new words. Those are going to be conditional statements in our class that we're going to assume to be true. So the corresponding angles theorem is going to say if we have two parallel lines, then we know corresponding angles have to be the same. So you start out with, we know that parallel lines exist, and the conclusion from that is that these corresponding angles will be the same. That is a conditional statement. Properties are generally going to apply to just maintaining equality or congruence when we're performing operations. So reflexive property, SFO, etc. We have a whole bunch that we can use for properties when we're actually performing an algebraic calculation. All right, the order. I think this is the most confusing part for people because they know what they need to prove. They know exactly like the pieces that they need to get there. It's just the order. And I also think that this is what makes it the clearest. Once you figure out how to order these things, it all starts making sense and it feels more systematic than just randomly justifying things. So to proceed directly from statement to statement using the hypothesis and conclusion of each reason. So I'm just making up these two new theorems that you have. The Dalmatian theorem, which states that if something's a Dalmatian, then it's a dog. And the dog-mammal theorem, which states that if something's a dog, then it's a mammal. Okay, so I'm just making up these two theorems to give you an example. It's very similar to what we are going to be doing now. And then I'm going to tell you what I want you to prove. I'm going to give you that Spot is a Dalmatian. Spot's a Dalmatian. I want you to prove that Spot is a mammal. So in this proof, our first reason or justification is going to be that this information was given to us. I don't truly know that Spot is a Dalmatian aside from just being told. So that's given to us. Now I want to make my way to show that Spot is a dog. I'm using the first piece of information that Spot's a Dalmatian to prove that Spot is in fact also a dog, which is exactly what's said in the Dalmatian theory. Something's a Dalmatian, then we know that it has to be a dog. So I'm justifying this step using this reason, the Dalmatian theorem. The Dalmatian theorem justifies that step in saying that Spot also must be a dog because it says that if something's a dog, if something's, a Dalmatian, then it must also be a dog. So I'm told Spot's Dalmatian, I know Spot's also a dog. Doing the exact same kind of thing with the next part. Spot's a dog. That's the hypothesis of that statement. Then I know I can also conclude that he's a mammal. So by the dog-mammal theorem, I know that Spot has to be a mammal. He's a Dalmatian, he's a dog. If he's a dog, he's a mammal. It's basically combining our laws of logic, the law of detachment and the law of syllogism, to get down to a full proof. We just have to state each part of that. I think this diagram also shows that pretty well. Spot's Dalmatian. That becomes the hypothesis of this reason. We're looking for a theorem here, or a definition here, that starts with this. And then here, we're going to look for a reason that starts with this as my statement. That's the assumption coming into this step. That should be the very first part of it. That should be the hypothesis. leading me to another conclusion, which in this case is exactly what I want to prove, that spot's a mammal. So each given statement is then used as a hypothesis to make a conclusion. You keep doing this until you prove what you need to prove. QED is Latin for, I think, that which was demonstrated. It's just saying, I did it. I proved that. You don't need to write that. It's just the end of proof. So definitions are a little bit more versatile. We didn't have that in our example, but definitions are a little bit more versatile because conditionals and their converses are true, so you can use them a little bit more flexibly. They can go either direction. We'll get into an example like that. For now, I'm just going to unload a whole bunch of theorems and definitions on you. You have access to these. You're going to be able to use these on our tests. When you get to the SOL, you won't actually have a word bank like this. It'll be a little bit different. It'll be just part of the multiple choice question. But for us, in a free response question, you're just going to have a word bank that includes all of our definitions, theorems, postulates, all of these things. You don't really need to memorize them. But I would encourage you to know how to use them, because if you get to the test and you don't know how to use them, using that word bank is not going to be helpful. It's just too much. It's going to be overwhelming. This is like half of what you're going to have for the first test. There's going to be way too many for you to figure out on the fly. You need to know how to use them beforehand. That's why I'm giving them to you as a word bank. It really won't help. You need to know how to use them. So most of these are conditional statements. All of these theorems and postulates are going one direction. You have to be given this information so that you can conclude the conclusion, the second half of that statement. The two definitions go either way. If I know that something is 90 degrees, or two angles add up to 90 degrees, then I can call them complementary. Or if two angles are called complementary, then I know they have a sum of 90 degrees. That can go either direction. All right, let's just jump into one here. So again, I'm going to start with one statement and use that as the hypothesis for the next reason. L is parallel to M. That's given to me. I want to prove that angles 2 and 7 are congruent. Angle 2. Actually, I do want to point out something about the way this is written. A lot of the times you'll see it written as the measure of angle 2 or the measure of angle 7. That little n in front just means the measure of those two angles. But we're trying to prove that 2 and 7 are the same. So those are alternate exterior angles. They're on the outside of these two parallel lines. I'm going to mark those as parallel because that's what I was told. I'm not assuming that. I was told directly that those two are parallel. So I know that these two angles are congruent because they're alternate exterior angles. I really just want to say that. I just have to use the right phrasing. By the alternate exterior angles theorem, I am justified in saying this. So this is, given that two lines are parallel, I know that these two alternate interior exterior angles are, well, that's just not correct, sorry, congruent. Alternate interior angles, sorry, this is just written incorrectly. Those are congruent. Those two are okay, those are supplementary. Corresponding angles are congruent. Sorry, everything else is right. That should read congruent though. Sorry, one more time just to get that on the clean start. L and M are parallel. That's what this is saying. That's the beginning of this statement. Two lines are parallel. Then I can conclude alternate exterior angles are congruent. That's exactly what I'm saying here. These two alternate exterior angles are congruent. So, by the alternate exterior angles theorem, I'm justified in making that step. All right, looking at number 2, angle 6 and angle 4 are supplementary. L is parallel to M. That's what I want to prove. So my given statement is that 6 and 4 are supplementary, and I want to show that these two lines are parallel. So you got to look carefully at these statements. This one's a little bit tricky because it's actually not one of the hypotheses of these statements. It's actually the conclusion of one of these. The only time I see supplementary in my word bank here, well, besides the definition, is in these two theorems, but it's at the conclusion. I want to work backwards, saying that, well, I know that these angles are actually going to be supplementary, and I want to work backwards to show that they're parallel. So first off, let's think about 6 and 4. Those are on the same side, and they're inside the parallel lines. So those are consecutive interior angles. So I'm working with this one, but I'm told that the conclusion is true. The converse is also true, though. I can go backwards here. I can say that since they are supplementary, we know that they're parallel. So we're going to say the converse of the consecutive interior angles theorem. If you say the consecutive interior angles theorem, that's not correct. It's going the wrong direction. That's starting with parallel lines, showing that they're supplementary. We do know that it's true, going the opposite direction. If we have two consecutive interior angles that are congruent, we know that these lines are going to be parallel. So we know the converse is true, so we can use that going the opposite direction. We could say that since we know this part is true, we can say that these two lines are parallel. Angles 3 and 5 have a sum of 180 degrees. That's given to us. And eventually we want to work down to L being parallel to M. So 3 and 5, those are consecutive interior angles again. And eventually I want to work my way down to two lines being parallel. So it's kind of similar to this, where I have supplementary angles and I'm getting to parallel lines, except I'm missing a step in there. This is just talking about them having a sum of 180. This does not use the word supplementary. So you have to be careful here because actually this definition uses the word supplementary. It doesn't mention a number at all. The number 180 is actually not that helpful for us right there. It's going to be a step in between to get us to supplementary. That's a frustrating step for a lot of you because it's like, it's so evident to you that obviously they're 180, so they're supplementary, so why do we need to say that? Because really it's not explicitly said in this definition. There is no number in this definition, but there is a number in this definition. So if angles are supplementary, we know that they're going to be 180, and if they're 180, we also know that they're going to be supplementary. So by the definition of supplementary angles, I can say that these are supplementary. So angles 3 and 5 are supplementary by the definition of supplementary angles. I'm also always okay with you abbreviating it like that, as long as it's very clear. Like if it's ambiguous, if it could be interpreted as two different theorems or definitions, it might not be okay. But if it's very clear, that says definition of supplementary angles, that couldn't be misinterpreted. I'm okay with you abbreviating it like that. That's what allows me to say that they're supplementary. And now if I know that they're supplementary, I can use the converse again, going from them being supplementary to these two lines being parallel to say that L and M are parallel. So the converse one more time of consecutive interior angles. That tells us that those two lines have to be parallel. Again, it's working backwards. We're given the conclusion you're working your way backwards to the two lines being parallel, which is the hypothesis of that theorem. All right, this is a lot. Try your best in the practice. Keep referencing the notes, keep asking for help, work together. It's going to take some time and patience, but you will get it.